So in this little film, I'm going to be recording some of the simulations that we're going to be using in this gravity and satellite motion lab. And so we'll begin with gravity. I'm opening it up with a flash player called a media, and you can do that also if you want. So basically this shows you how the law of gravity works, how the gravitational pull on this rocket decreases as it moves further away from the Earth. So right now it's right on top of the Earth, so it's at a distance of one radius here, one radius of the Earth. Now I'm going to pull it away just a bit, and you can see right now it weighs 1 unit, whatever this is, units are 1 ton or 1 pound if it's a toy rocket. So let's see what happens as I pull it away. And you can see it over here, that right now the distance is 1 Earth radius. Now if I pull it away, it's a little more than 1, a little more than 1, a little more than 1. I'm going to get to 2 Earth radii away. Okay, eventually. I want to do it bit by bit. Right here. So it started, it weighed 1. What does it weigh now? Well, if you look up here, you will see it weighs about that much. Don't forget, this is 0.1, 0.2, 0.3, 0.4, 0.5. So right now it weighs about 1/4 of what weighed up there. We keep going, for example, and eventually we're going to get to 3. Right there. Okay, 3. How much does it weigh now? Again, take a look here, how much it weighs now. And you can do it with 4 and sort of figure out what it would be for 5. And if you draw the curve, you can see how the curve drops down, how the force drops down. Okay, so the next one would be, I call the cannon. So imagine that I'm on top of a big mountain and I have a cannon. I'm going to fire the cannon out. Let's see what happens. So right now, let's say I'm going to fire it out with a velocity of 2 kilometers per second. So the cannon goes this way and hits here. How about I try it with 4 kilometers per second. Reload, fire again. Well, it goes a little further. Well, I wonder, let's try 6 kilometers per second. I wonder if it'll ever go around the Earth. Not enough, right? Let's try 8 kilometers per second. At 8 kilometers per second, oh, look, this doesn't make it. I'm sorry, I had 7. At 8 kilometers per second, it does make it. Now, in this simulation, it makes it in 7 seconds, but in real life, it's 85 minutes. It takes for this ball to go into orbit around the Earth. So every satellite goes around in this orbit. Okay. So let me try now. We're going to do orbital velocity. We're going to look at the same thing from a different point of view. Okay, this is the one I'm going to open. So basically in class, we saw that. Let me go here. That orbital velocity, the velocity something has orbiting, is given by this formula over here. Okay, and this applies to satellites orbiting the Earth or all the planets orbiting the sun. So we're going to look at what happens if we go to another planet where the mass of the planet is not the mass of the Earth and the radius of the planet is not the radius of the Earth. So let's do that. Here's the formula that we're talking about. This is called the centripetal orbital velocity. And what would happen is if we, for example, change, and this is a planet orbiting the sun, not a satellite. What would happen if we changed the sun's mass? For example, what if we made it bigger? If you look at the formula here and the formula over here, what if we made the mass bigger over here? What would happen to that velocity? Well, the numerator of this fraction is bigger. So what would happen? Well, it should get bigger. Let's see. Let's make it, instead of 1 solar mass, let's make M 2. Look at that. It's now twice what it was. I'm going to replace this with 2 instead of 1. It's 42 kilometers per second if the sun was bigger. Let's put it back at 1. Oops. Let's put it back at 1. And you see originally it was 30, and now it's 42. What if we triple the mass of the sun? Okay, make it 3 times as big. Look at that. It's now 52. This becomes 3. So let's put it back to what it was, 1. What if we take the orbit of the planet Earth? What if the Earth wasn't orbiting here? This is actually one astronomical unit. This is how really the Earth is. That means it's going about 30 kilometers per hour. That's the velocity. What if we wanted to have if the Earth was further away? Let's say 1.5, 1.5. You notice what happens here? We replaced R here with 1.5. And you can see, because we made the denominator bigger, the velocity became smaller. Okay, when it was 1, the velocity was 30. When we made it bigger, the velocity got smaller. You can see it changing there. Look over here. And if we made it smaller, the velocity gets bigger. Look how fast it's going when it's close. So let us now look at one more. The one on escape velocity. So again, we are on Earth, and we're going to try to fire this out and this sideways at the same velocity to see what happens at escape velocity. The formula for escape velocity is given on top here. So we know what the answer is. If we use 1 for the mass of Earth, r for the radius of Earth, both of them are 1, then in this formula it's 11.2 kilometers per second. But before we do that, let's fire it out with a velocity that's smaller than that. Let's say not 10 kilometers per second. All right, so we know it's not enough to escape, but let's see what happens. Let's fire it out. What happens is that the one fired out perpendicular is going in orbit around the Earth, but not in a circle, in an ellipse. But the one that's fired out comes back down. Okay. Let's reset it. And now let's fire it out with just a little bit bigger than the escape velocity. And we see that the velocity does not, the rockets do not come back. So let's take a look what would happen if we change something about the Earth. So for example, if the Earth was smaller, same mass, but the Earth the radius was smaller. That means we're going to make r not 1, but we're going to make it less than 1. Let's make it, let's say, a half. Okay, so if we made this smaller, the escape velocity gets bigger. The denominator of a fraction is smaller. The escape velocity becomes bigger. So we would have to fire it out now, not at 11.3 kilometers per second. We would have to fire it out at 15 kilometers per second. We can't quite make it 15. So what I'm going to do is I'm going to make it a little bit smaller. We can fire it out at 14 and a half. So I'm going to make it about not quite half, at 0.6 smaller. And let's fire it out now with that velocity of 14.4, 14 point, a little bit bigger than that, 14.5. So let's fire it out and see what happens. And you can see what happens is that it does not come back. Now in this simulation, you can go also to other planets. I can reset everything. In other words, turn back the Earth's mass, make it 1. Yeah, the Earth's radius, make it 1. And then we're going to go to another planet. We're going to go to Mars. Now Mars has a different mass. In fact, Mars is the mass of Mars is about 1/10 that of Earth, and its size is about 1/2. So if you were to use that formula, the escape velocity would be 5. So we can actually make it a little more than 5. We would escape with that velocity. Let's reset it again. Let's go to Mercury. All right. Escape velocity is 4. Okay. So let's fire it again. We didn't fire it fast enough. You notice we only fired it at 2.937. So let's see if we can change that. It's 4, so we need to fire it at least 5 kilometers per second. And you see it escapes. You can do the same thing with some of the other planets. For example, you can make this Venus. All right, Venus has a mass of very close to Earth, a little bit less than Earth's in size. They're very close in size, about 80% mass and about 95% the radius. They're almost the same. So the escape velocity is pretty close to Earth. So don't forget it, for Earth it was 11.2. And so we're going to require to escape from, we're going to have to fire it at 10.4, a little bit more than that. So now you can see that it escapes. And if we fire it a bit less than that, for example, just 10 instead of 10.4, You see, it should not escape, should eventually come back. Almost escapes, it's pretty close, but it almost escapes and we come back. Eventually it will come back. It's not going to make it around. All right, but it's going to come close, you know, it's going to come close because we're pretty close to the escape velocity. 10.1 as opposed to 10.4. That's it, it's going to stop right now. And presumably come back. Now the orbital one will orbit because this is orbital velocity, doesn't have to be that big, so it'll keep going, but notice this starts coming back. So let's look at the algebra problem using the algebra simulation. For example, let's do this using this simulation here, and then we'll do it this way. If a woman weighs 100 pounds and she went to a planet that was 3 times as massive as Earth, how much would she weigh there? Well, let's take a look. 3 times as massive as Earth. Let's go to the simulation here. Okay, so F is 100 pounds. If she went to another planet that was 3 times as massive, then she would weigh 300 pounds. 3 times F, okay? How about some of the other problems here? A woman weighs 100, she went to a planet 3 times as massive as Earth and 2 times the size. Let's see. So she weighs F, 3 times as massive and 2 times the size. That means you got to square this. This would be 3 divided by 4, 2 squared. She'll weigh 3/4 of 100. Don't forget F is 100. Okay, 3/4 of 100 means 300 divided by 4. How about this other one? She went to a planet that was 3 times as massive and half the size. All right, make this half. Oh, she would weigh 12 times as much. That means 3 divided by 1/2 squared, which is 1/4, which is 12. So she would weigh 1,200 pounds. This is 12 times 100. How about the next one? She went 3 times as massive. Okay, we have that, but 1/3 the size. So we're going to change this to 1/3. Don't forget, if you square 1/3, you get 1/9. 3 divided by 1/9 is 27 times F. Don't forget, F is 100, so she would weigh 2,700 pounds. How about on the last one? If she went to a planet that was 1/2 the mass of Earth and 2 times the size of Earth, how much would she weigh? 1/2 the mass, all right, let me change this to 1/2, and 3 times and 2 times the size, maybe change this to, she would weigh 1/8. 1/8. Okay, and this is 1/2 divided by 4, which is 1/8.